developer advocate with AWS, and I've spent most of my adult life building and operating applications. And over that time, everything has become more and more complex. So thinking about how to make applications more reliable and resilient has really become an important part of what we as builders do. So tonight, we're going to be talking about a new service that we launched at AWS reInvent 2020, and that is called AWS Fault Injection Simulator. And that is our fully managed chaos engineering service. So some of you might know what chaos engineering is, some might, or for some it might be a totally new concept. So we're going to go through this from the beginning, look at what the problem is, how we try to solve it, and then gradually going to more and more advanced things around chaos engineering. So let's start off by looking at what we'll look at. I want to talk a bit about the challenges we see with distributed systems and why chaos engineering has emerged as a really great solution for dealing with the complexity and the uncertainty of these complex systems. So we're going to go through the challenges that we see customers face when they start their chaos engineering journey, because a lot of customers are using chaos engineering already. And we are then going to look at AWS Fault Injection Simulator, or FIS. And of course, we're going to look at what features there are and different use cases for using chaos engineering and FIS. And along the way, a bunch of demos using this. And in the end, I want to look at doing automated chaos engineering experiments, how we can use AWS FIS for that. So that's the last part of this session. All right, so let's start with the challenges of distributed systems. And the benefits, they are really clear, why we want to use distributed systems. And using it has really revolutionized the way we build systems and applications today. But some of the challenges are, for instance, latency, scalability, reliability, resilience, concurrency, and designing different APIs, how we use marshalling and unmarshalling data, and complexity in using different algorithms. So as our systems, the systems we build, as they grow larger and more distributed, what starts out as perhaps a theoretical edge case can turn into real occurrences. And in the end, that complexity can turn into failure. So while most people understand that distributed systems are complex, it's a mistake to think that this complexity only applies to applications that have hundreds or thousands of microservices, because this also applies to smaller systems that we build. So even the small systems that we build are complex. So for instance, a simple client-server communication, there are a lot of steps involved to successfully complete just a single round trip. The client puts a message onto the network that is delivered to a server. It validates the message. The server updates its state, and so on and so on. So there are a lot of steps involved in every single network call that we do. And when we consider all of these permutations of failure that can happen in these very simple distributed systems, especially when we're talking about multiple requests. So think about what it looks like when we have thousands or perhaps millions of requests. And the traditional way of tackling this has been to do testing. And as our systems, our distributed systems, have grown more and more complex, testing has really reached its limits. And often we only implement tests after an outage has occurred in our production environments. And when that has happened, well, it's already too late. So Testing, well, that is of course mandatory, and we shouldn't stop doing testing, but it doesn't apply well for distributed systems, and often it doesn't address the complexity with these distributed systems. So testing, it tests things in isolation, and it really verifies only the known conditions. So it answers different questions like, is this what we are expecting, or is the result of function X, Y, and so on. So what about all of these random failures and other weird errors that happen on networks like the internet? How about different configuration limits with services and the drifts all along as we iterate on our applications? And what about all of the unknown things that we don't know about? How can we test for something that we don't know yet? And of course, some things are just really hard to test. And for example, in a system where instances start and stop dynamically, what happens if any of the instances run out of disk space? Well, I think a lot of you who have built systems using virtual machines or instances have faced disk space failures in one form or another. And debugging apps that run out of disk space, it's pretty hard. So it's a pretty common issue that happens when there's no log rotation, for instance. And to make things even more complicated, you can get these no space left on device errors when there's still plenty of space left on the device. For example, when the file system has run out of inodes because too many files have been created. So the problem with testing these type of failures is that it's localized and isn't something you catch during normal testing. So when you have these disk space failures, well, what happens then? Well, you have to start thinking about implementing fixes for this with log rotation, using different centralized log services, monitoring disk space, and so on and so on. But to find these kind of unknown failures before they happen, there is, of course, a practice that helps us find these. And it is, as you probably guessed by the name of this session, chaos engineering. So chaos engineering is the process of stressing an application in production environments by creating disruptive events such as server outages or API throttling. And I say production environments, but we shouldn't really think about chaos engineering only for production. We can do it in testing, in staging, in development environments as well. It's also about observing how the system responds and implementing our improvements. And we do that to prove or disprove our assumptions about our system's capability to handle these types of disruptive events. But rather to let those events happen in the middle of the night or during the weekend or anyone's holiday, we want to create them in a control environment and during working hours. So people are there to actually find out what the issue is and create a fix for it. And it's important to note that chaos engineering isn't only about improving the resilience of your system. It's also about improving resilience, uncover these hidden issues, expose blind spots in monitoring, observability, and your alarms, and a lot more. Improve recovery time, improve operational skills, the culture within your organization, and so on and so on. So it's really important to understand that chaos engineering is not about breaking things randomly without a purpose. Chaos engineering is about breaking things, but in a controlled environment through well-planned experiments in order to build confidence in how the application and the tools you're using can withstand these turbulent conditions. And to do that, we follow this well-defined scientific method that takes us from understanding the steady state of our system to articulating an hypothesis, running an experiment, often using fault injection, then verifying the results of that experiment, and then finally learning from the experiment in order to then improve that system. And improvements such as its resilience to failure, its performance, the monitoring, and so on and so on. the overall system. But while chaos engineering is a really great to have option in our toolbox when we build and run systems, many of our customers have told us that it's really hard to get started using chaos engineering. It's hard because you, in many cases, have to stitch together different tools, use some scripts, libraries to be able to cover that full spectrum of faults that you can inject into a system. And you have the infrastructure, you have the network, the application. Each often has different tools to do the job, whether it's a library, a script, or an agent. And many of our customers, they don't really want to install anything extra in their applications. More things to install, well, that equals even more complexity into an already complex system. So it's also difficult to ensure that we have a safe environment where we can inject our faults. And ideally, you also want your tools to automatically stop and roll back if any alarms are setting off. So you also want this to integrate nicely with the monitoring solution you're using. And finally, some failures are just really hard to reproduce. So it's important to realize that outages rarely happen because of one single failure. It's often a combination of small failures happening at the same time or in sequence. And that is often just hard to reproduce. So we are very excited to introduce the new service that we launched at AWS re:Invent, AWS Fault Injection Simulator. And as I mentioned, that's our managed chaos engineering service. And we want it to be really easy to get started using this service to then produce real-world failures, whether they are simple, like, for instance, stopping an instance, or more complex, like throttling APIs, for instance. AWS FIS really embraces the idea of safeguards, which is a way to monitor the blast radius of the experiment and stop it automatically if alarms are setting off. So getting started should be easy, and it is easy. And this is something we've really put a lot of effort into. So our customers have repeatedly told us that it was hard to get started with chaos engineering. So we wanted it to be easy. And you can use the console, the regular AWS console, to get started and get familiar with the service, try things out. And then you can start using the AWS CLI to take advantage of templates and integrate this with your CI/CD, for instance. And the templates are either JSON or YAML that you can share with your team, and you can version control them and to benefit from all of the best practices associated with code reviews. So when we run our experiments, we can either run them in sequence or in parallel. Sequences, they are often used to test impact of gradual degradation, like sequence of actions to gradually increase latency. And parallel experiments are to test impact of multiple concurrent issues, which, as I mentioned before, is often how real-world outages happen. And supported services right now are Amazon EC2, RDS, ECS, and EKS, and a lot more services will follow. We're working hard on getting more services into the service. So you can create quite complex conditions that span across a large set of different AWS services. And I think it's really important to think about that these faults that we're creating, they are really happening in your application, in the environment you're running them on. And they are run at the service control plane level at AWS. So an instance is actually being terminated if that is your action. Memory is actually being utilized, and APIs are actually being throttled. So we're not faking it. We're not trying to just show what could happen. This is actually what is happening to your environment. So you always use extra caution with chaos engineering. Safeguards, then, they act as this automated stop button. So it is, as I said before, a way to monitor the blast radius, that is how big that experiment is, and make sure that it is contained, so that the failures that you create with the experiment, they are rolled back if alarms go off. We don't want to break things. We want to learn about our environment. So safeguards is a really important part. We can also use IAM controls to control what type of faults we can use, what resources can be affected, and of course, who can use this service. We can use tag-based policies and filtering and so on. So this is just a simple overview of this service, what it looks like. And we can use FIS, as I said, through the console or through the CLI or through the SDK. And the console, as I mentioned, is great to just get started using the service. It integrates with IAM and with the policies that you're familiar with if you're using AWS today. So you can make sure that it is contained just as you want it to. And when you create your chaos experiments from the console, FIS will automatically create these templates for you, and templates that you can reuse later on. And once you start your experiment, FIS will then inject the real failure, into your AWS resources. And once again, we have CloudWatch alarms in place to be able to have these safeguards to stop the experiment automatically if needed. All right, so to use the service, there are
I think we lost Gunnar. Gunnar. Man, we were just getting to the good part.
Yeah, I was actually busy typing him a question, which I hope he'll be back and answer. Let me just post it now, Rian. You're right, it's getting very interesting. Okay, and maybe we can just save that for when he's back. People have been asking around notifications when you run your experiments, but he'll look at that when he actually logs back on.
Do you maybe know if ECS is also supported?
ECS is, and I know EKS is. Yeah, I think ECS and EC2 and RDS is supported. Hi, Gunnar.
It wouldn't be a chaos engineering session if something didn't go wrong, right? So I just injected fault into my Chime client, but now we're back. All right.
I think it might be because we are in South Africa, and I see it actually chose South Africa.
That's right.
Yeah, you have the highest latency of all of us.
I am far away from South Africa. So let's start sharing my screen again. Was there any questions in the meantime? Or did you answer those, Felisa?
No, I didn't. There is a question that I've posted. I just need you to just double check for me. I saw someone asking around direct integration with SNS for notifications. And I think the response from the engineering team was there isn't, but I see there is. You just said now there's integration with CloudWatch. So that would take care of the notification side of things then, because through CloudWatch, you would do your notifications, right?
We based on alarms, for instance, we could do that, but there aren't any other notifications we could use that way through CloudWatch at the moment. But it's something that they are working on, as you said, Felisa.
Sure.
Right. So you can see my screen, hopefully, again. And the actions, as I said, those are the actions that we will inject, the faults that we will inject when we're running an experiment. And they contain the fault type, the duration we want to run it for, the resources that we're targeting, and timing relative to other actions, for instance, but also rollback behavior for specific fault types or action types. And this is just a basic JSON representation of an action. We have two different actions defined. We'll look at these again later on. Stop instances and wait action. And wait in this case is ordered to execute after a stop instances. So this is a sequential experimentation execution. Some of the actions that we run, they are performed through the AWS Systems Manager agent. And the SSM agent is pre-installed on most Amazon Linux and Ubuntu images. So we will use that agent to perform certain tasks or certain actions. Next, we have the targets. So those are basically one or more AWS resources which we're carrying out an action on. So we define targets when we create our experiment template. And we can use the same target for multiple actions within that same template. And they then include the resource type, the resources themselves, that could be the resource ID, using filters, tags, and so on. And then also the selection mode. So if we want to target all of them, or random selection, or a specific number. And this is the JSON representation of targets, where we're using filter to target only instances that are running in a specific availability zone, for instance. We can also add tags to refine that selection, so we can specify tags on certain EC2 instances that are chaos ready, for instance. Next, we have the experiment templates, and they are that template that define the entire experiment for us, and they are used when we're starting our experiment. So they contain the actions, the targets, any stop condition alarms that we're adding as safeguards, which IAM role to use, which is a role to then be allowed to run this experiment, and any tags or description we want to add as well. So this is a complete template, small print right now, but JSON, YAML, any way you wish, and we can then edit this either through the console with the UI, or we can use it as YAML or JSON and edit it in VS Code or any other IDE that we're using. So we can run experiments like the one on the left, sequential, where we have specific targets. Or we can then create these more complex experiments running in a mix of sequence and parallel, and use very advanced filtering for our targets. And for both of this, once again, make sure to use alarms, especially if we're running these experiments in production. So we really have the full power of AWS FIS that way. The experiment was the last part of AWS FIS that I wanted to point out, and that is simply a snapshot of the experiment template when it was launched. So look at this as the history of your experiment, the execution of that experiment. So it adds some additional information, the creation start time, and the status, the execution ID, and so on. So right now, we have this list of faults available in AWS FIS, but the engineering team is working hard on adding additional ones. They are, of course, based on the services I mentioned before, EC2, RDS, EKS, ECS. And we're adding new fault actions throughout the year with AWS FIS. So I want to talk a bit about use cases for this. So what we typically see our customers doing is to run these as very often one-off experiments, where we do experiments, we create our experiment template, we define a specific target that we want to use it on to verify something. We've created that hypothesis that something should act in a certain way, and we create that experiment, run it to then either prove or disprove that hypothesis. And if my EC2 instance named X goes down, this should happen. We run the experiment and we verify that behavior. That's a very common way to at least get started using chaos engineering. What's also very common is to run it as these periodic game days. And a game day, if you don't know what that is, it's the process of rehearsing ahead of an event, usually by creating these or creating the anticipated condition, and then observing how both the system and the team responds to that action. So using chaos engineering in game days, it's a very common practice and something that Amazon and AWS has been doing for a very long time. Ben Robbins started it all at Amazon way back when, and this is something that we also try to encourage our customers to do in the same way. And these events, well, they can be, for instance, an unusually high traffic day, a new launch, a specific failure that you've observed before, or anything else. And using chaos experiments this way, it means that we can create these event conditions and then monitor the performance of the system and the team. So having these two ways of getting started, well, that's great. That means that we have a good basis to get started doing chaos engineering. And now, unless there are any questions we should take straight away, I want to jump into showing a bit of AWS FIS. I take silence as a no. So, all right. So first off, I want to show you a very basic example in the console, and then later on we'll get to some more complicated experiments using the CLI as well. So the first one is using the AWS FIS in the AWS console and stopping an instance. Oops. Mm-hmm. There we go. All right. So this is the AWS FIS service in the console. So let's start to create a new experiment template. And the first step then is to add some sort of description for our template so that we know when we have this long list of templates what this specific experiment does. We then select our IAM role, and this is a role that should then have the correct permissions to run that experiment. Next, we add an action, and we give the action a name, stop instance. We select the action type, in this case, stop instances for the EC2 service. We select a duration that this will run for, in this case, 1 minute. It automatically creates a target for us. And we're saving that before editing our targets and then adding what instances we should run this on. In this case, we're going to use one specific instance. We could add multiple instances. We could add using filters and tags and so on as well. And this is our instance. It is running. And this is where we would add stop conditions, not doing that right now. And as we're not doing that, we are getting this prompt that do we really want to create without the stop condition? And in this case, yes, we will. So now we have our experiment template created. This is the ID of this specific template. And we can now start our experiment. And we need to confirm that we want to start because this will actually inject fault into our environment. So the experiment is running. We can check the status of our experiment. Looking in the EC2 console again, we can see that that specific instance is now stopping. It still has the pending state. Is this specific target? Go. It is the target. The instance is now in a pending state. Let's refresh again. And now it's starting again because we set in the template that this instance should start again. Now the entire experiment is completed. The instance was stopped, and after 1 minute, it was started again. So that was the experiment that we ran this time. Here we go. So that was our first experiment, a basic one where we simply stopping an instance and then starting it at the end. And by doing these kind of experiments, we're able to test certain things within our environment. What happens to the system if an instance disappears this way? In this case, it stops and then starts again. Next, let's do a stop instance again, but by using safeguards, adding alarm to this. So now we have a CloudWatch alarm set up called network in abnormal. It is right now in the OK state, and it has a threshold set up and for when it should go into that alarm state. So now let's update our experiment template. And under the stop conditions, we can then enable this CloudWatch alarm. Now we've added that as a stop condition, meaning that if this alarm sets off during the time we're running our experiment, the experiment will then be stopped and FIS will try to roll it back. All right, so we can see still that EC2 instance is running. So let's start the experiment again. Once again, confirming that we want to start the experiment. The state now says that it is running. The action is pending right now, so it should start really soon. Our stop condition is in place. So now the instance is stopping. It is now stopped. And this is our alarm. This alarm doesn't really have anything to do with that specific instance. But what we can do with the CLI is to set the alarm state of our alarm. So we're setting it to the state value of alarm, meaning that this is, we're just testing how that alarm would work. So now it's in the alarm state. But think of this as it could be any type of alarm we have set up. So now, pretty much straight away, AWS FIS will then stop that experiment. And our EC2 instance is starting again. As we can see, the experiment has failed. The experiment is stopped by AWS FIS. And as we saw, that EC2 instance did start again. So that's an example of using these safeguards, CloudWatch alarms, together with our experiments. So think of this as, for instance, you have a website that should be running if something is happening and an alarm triggers. For instance, you're using a canary in CloudWatch, watching that start page of the web page. If it goes into an alarm state, it could then stop that experiment before users are affected or have a bigger outage of your system. Right. So next, let's also look at how we can use filters and alarms in our experiment. So as you can see, we have a bunch of EC2 instances running US East 1, A, B, and C. This is now in VS Code, our experiment template. We're using JSON. So we have the CloudWatch alarm in place. We have targets. And in targets, right, the instance first. And in targets, we have filters enabled. So we can filter out based on a specific availability zone in this case. So let's create this experiment template based on that JSON file. Going back to the FIS console to have a look at it. We have our specific experiment template. So by using the JSON file and the CLI, we can create the template that way. And we can see that it has two filters in place, one for the availability zone and one for a tag, the purpose. So now we can use the CLI once again to then start our experiment based on that experiment template we just created. And we will then get a response from the CLI showing that it is running. And as we can see straight away, all of the instances that match that filter, the ones that are in US East 1B, they are now stopping. So looking at this experiment, we have an experiment running, stop instances for 2 minutes. This is our CloudWatch alarm again. So let's set the alarm state to alarm, as if something would happen to our application or system running. It is now in an alarm state. And the instances straight away go to the pending state because the experiment is stopped. It is failed because of that alarm that triggered our stop condition. So now the instances are starting up again. So that was an example of how we can use filters to specify specific instances, in this case based on the availability zone of those instances. So we can then simulate certain type of failures that way, create our hypothesis based on that something happens to instances in US East 1B availability zone. All right, so next, I want to show you an example of doing something else than stopping instances. I want to show you CPU stress fault injection. So in this case, we have our JSON file with the template. We are pointing to one specific instance. And we're using an action that's called the SSM send command. And there we're able to use a document, an SSM document that's available called as CPU stress. And this document contains information about how we can then use, in this case, CPU stress on our instances. And this is then run by this SSM agent. So there are multiple of these different documents available publicly, but you can, of course, create your own documents as well. This one will run for 120 seconds. And we also have that stop condition in place. So now let's create our experiment template based on that JSON file. Right, so that is created. Next, we can take that experiment template ID, logging into the EC2 instance. Just checking that it is the same instance. It is. All right, so watching for the stats on that server when we now start our FIS experiment. started the experiment. It's still in a pending state for a short while. Go. But now on the instance, we can see that CPU levels are going up, and it has now reached 100%, meaning that this action is running on that instance, and the instance is then having a CPU stress. Stopping the experiment will then also stop that CPU stress. So this could be a stop condition using an alarm to make sure that if we're running this experiment and things start to break, well, we can then abort that experiment using that stop condition. All right, final demo right here. It is using what we call API throttle errors. And API throttling is something that I think is really exciting because it means that the things we've done so far, they've been basically things that you could do using either the AWS CLI or straight on the instance by stopping an instance. You can even do it in the console. But API throttling means that we can throttle the access to certain APIs and that is happening on the control plane level, meaning that we're throttling access to certain APIs in a way that you really can't do any way by yourself. So doing these actions means that we can really simulate certain type of failures that could potentially happen in an environment. So let's have a look at that. All right, let's try it out. So what we have here is, do we have something there? Yeah, we do. This is an experiment template where we will throttle the EC2 API. And we will throttle two certain operations, describe instances and describe volumes. So this is within our experiment template. So based on that, we're creating our experiment template based on the JSON file. There we go, that is created. Can now use the template ID for starting our experiment. And this will then throttle the EC2 API for describe instances and describe volume operations. So logging into the EC2 instance, let's just double check that the experiment is running. It is running. And then on that instance, running that command through the AWS CLI, EC2 describe instances. Normally, we would get a pretty quick response with the available instances. In this case, we're getting an internal error when we're running describe instances because that API is throttled for that specific instance. It has done its 4 retries, but we were unable to use that API. So now let's stop the experiment. Check to see that it's stopping. It is. And now let's try it again on the instance, and we're getting a reply. So by using API throttling, we're able to limit certain operations and think of operations that you might use. For instance, you're having some sort of, you're using the EC2 API for something within your application. Well, by throttling that, what happens to your application in that case? Do you have fallbacks in place so that you're able to still have working app without reaching that API? And at the moment, this works for the EC2 API, but we're working hard on getting more APIs in place so that you can start using this for other services as well. Okay, so now that brings us to the last section, which is around automated experiments. And you remember this from early on in the session. We talked about the scientific method of doing these experiments. And this is really a great way of doing these experiments. But when we do these, well, it is a manual process. We need to do them over and over again, which takes time. And it's really hard to think about all the different ways a system can change over time. We have drift, we add new functionality, we add new services and things like that. So automated experiments is a way to perhaps handle that complexity in an even better way. So doing these automated experiments, it goes back to the scientific part of chaos engineering in my mind. Repeating experiments is standard scientific practice for most fields. So we can repeat experiments more than once to help us determine if the data was a fluke or if it represents the normal case. And it helps us guard against jumping to conclusions as well without enough evidence. And automation also helps us cover a larger set of experiments than we can cover manually. Automated experiments also verifies our assumptions over time as unknown parts of systems change as well. Think about a system with multiple microservices. Perhaps different teams handle different parts of that service. So what happens when service B changes or service X changes? What effect does that have on your system? So first off, we have what I call recurring scheduled experiments. We can schedule experiments and run them on a scheduled basis over and over again. So I want to show you an example of how we can do that. So functionality for this today isn't built into AWS FIS. So what I'm doing is I'm using the SDK that is available. So I'm creating, in this case, a SAM template. Big fan of serverless, so SAM is great for me. And I'm creating, I'm adding parameters first, but I'm creating a Lambda function that then allows us to run an AWS FIS experiment on a schedule. Adding an event trigger in this using CloudWatch events, and adding a schedule. I, of course, also want to add a policy to make sure that we can only run this for our specific experiment, this specific experiment that we want to try this on. So I'm adding that in the policy. I'm also adding an environment variable. And this is my Lambda function code. I'm using the new version 3 SDK and creating a new FIS client. I'm picking up that experiment template ID that I'm adding as a parameter in my SAM template. And then we can pass these parameters on to AWS FIS. So this is where we'd add our experiment template ID. And then basically using the FIS send command, I can then run a new start experiment using FIS. So that is the basic Lambda function behind it. In this case, I have a bunch of instances running in my sample app. This is my experiment template. I've set up to use filtering based on resource tags, sample app running in the staging environment, and I've added a filter for instances that are in the running state, and all of those instances. these are the actions. In this case, I'm running a bunch of different actions in sequence and in parallel. We're running it for 180 seconds. Using SSM send command, we're going to do a CPU stress for 60 seconds. We're increasing the CPU level, so we're gradually adding more and more CPU to our environment or to our running instances. And then, of course, we have stop conditions in place. I have three different even. Simple demo one, I have a synthetic setup, and one for CPU levels. So adding multiple stop conditions is quite common when we're starting to create these more advanced experiments. So now, creating that experiment template based on the JSON file, I can then pick up the ID of my experiment template. And deploy my SAM template. In the SAM template, I had a parameter for experiment template ID, adding that. And I'm using a CloudWatch event schedule based on a cron schedule expression. So it's going to run once a day at 12. And just running through the rest. Deploying that. All right. So looking at that Lambda function. Here we go. Right, so this is our rule based on a schedule. So this experiment will now execute at 12 p.m. GMT every day to run this same experiment with my multiple stop conditions if anything goes wrong, to be able to then catch drift and so on. So let's try it out. Just testing my Lambda function with a test event, which will then be the same as if this was 12 p.m. GMT. So now the Lambda function has succeeded. This is my experiment template. And my experiment is now running. So on one of those instances, we can straight away see that the CPU levels are going up. It is now at 100%. So this experiment is running there. We also had memory action to add or fill the memory of the instance. So it's taking these different actions and running those. So by running these experiments on a scheduled basis, we're able to pick up on changes perhaps. If this works just fine, day 1, day 2, day 3, and so on. But as changes happen within our application, perhaps something will change. There are differences happening that will then mean that we'll have another outcome after a while running these experiments. So that is why we want to do scheduled experiments. So next then, we have the event-triggered experiments. Event-triggered experiments, they are experiments where we can start the experiment in pretty much the same way as now. This was based on a schedule, but instead we can base them on events that happen. And an event could be pretty much anything. Think about things that happen within your AWS environment. An autoscaling event, for instance. So when something happens in your autoscaling group, well, that could trigger an experiment to run to see, does this work while we're having an autoscaling event, or while an instance is being terminated, things like that. So you can add these different events and trigger experiments based on those. And once again, to pick up on different things that might change over time in your environment, things that take too much time to do manually. And I want to jump into the last one then, continuous delivery experiments. And I think this is a really fun one, but also a very important one. So we work with continuous delivery. Many of us, we are able to write code and deliver code fast into our environments. But that also means that we're able to create this drift that I mentioned several times now. We're able to create these systems that are becoming more and more complex, and we aren't able to keep up with testing and by running our manual experiments. So adding chaos experiments to our delivery pipelines, that's a great way to be able to do these tests over and over and over again. So let me show you an example of that as well. So what I have here is a very basic pipeline in place using code pipeline. So it has different stages where we then first have the source in GitHub, we have a deploy stage, and it could be a build stage, and so on and so on. So once again, a SAM template that contains all of the code for my pipeline. So we have all of these resources gathered in the same. This could, of course, be somewhere completely different in a CloudFormation template somewhere. So we have this pipeline with our different stages. We have the source. We have the deploy stage. And then I've added an experiment stage. This is experiment to staging environment. And what we can do here then is add an action, which is a Lambda action. So we're invoking a Lambda function as an action within our pipeline. And we're running a function that's called pipeline start experiment. And we've added a parameter for our experiment template ID. Next, we have an action type for an approval step. So even though this is something that it will start our experiments automatically, we can still have an approval step so someone can check that it actually works as intended. So then we have the Lambda function. And this is pretty similar to the one we saw before. There are some changes, of course, because this one needs to be able to update our pipeline, the failure or success of our pipeline. So we still have a policy in place to be able to do that for our specific experiment template. Right? And this is the code for the Lambda function. A few more lines, still using the SDK for FIS, but also now the SDK for code pipeline. And then able to use the put job success or put job failure commands. Creating those clients. And then within that Lambda function, we can then pass on that experiment template to be able to start our experiment. We're passing on the job ID to make sure that we only start this experiment once. We then run the start experiment command. And based on the result of that command, we can then update our job within the pipeline with either success or failure if that experiment has started or not started, that means. All right. job failed. Second one. Now Rehan is in darkness. There we go. So closing that. Refreshing my pipeline. We can now look at the pipeline containing that experiment stage as well. We have the source, we have the deploy to staging environment, and then we have the experiment in staging environment, where it will then start the experiment, and then we have an approval step where we can approve if the experiment was successful or not, before moving on to deploying into production. So even though we're doing this in our staging environment, it will give us knowledge and we will learn things about our environment. So just doing an update in GitHub to that test application to kick off my pipeline. There we go, switching back to code pipeline. It is now fetching the source from GitHub and starting to deploy to staging using code deploy into my EC2 instances. Quick one, very small application. And now the experiment should start, because the start experiment staging AWS Lambda is now being executed. And it has succeeded. So switching to AWS FIS, we can now see that our experiment is running. The experiment that we have created based on our pipeline, that is then running on our staging environment. We then get prompted to do a review, to approve, to move on to deploying to production. We get a link to the FIS console and that exact experiment. And we can see that it is running, and we can check what we would do. Probably in this case would to look at perhaps logs, look at dashboards, whatever we feel necessary to check before we're able to then approve this. In this case, I'm satisfied because the experiment ran completed. The experiment succeeded, and I can approve. And next then, well, my pipeline moves on, deploying that same artifact into my production environment. So with that, we have a way of then doing these automated chaos engineering experiments in our pipeline. Next step, well, that perhaps would be to add the same type of experiment, but in our production environment as well. So when we deploy to prod, we would do the same type of experiment there. So those are 3 different ways of doing these automated experiments. We have schedule experiment, event-triggered experiments, and continuous delivery experiments. And with this, should we then stop doing one-off experiments or these game days? No, we shouldn't. That's still the core of our chaos engineering practice, in my opinion. So they are super important because it means that people who are involved in doing those, they learn a lot about both the system and in the organization, and it helps you build confidence. So if you want to know more, test some yourself. These are some resources around AWS FIS, and documentation, and some samples from the AWS samples organization in the GitHub repo. And then links to both of the examples I showed as well now with the scheduled experiments and the pipeline experiment. We can post these links, of course, as well. And with that, I think we're at Q&A. If there are any questions.
Yes, well, thanks, Gunnar. That was Actually, very interesting. I didn't even think of applying chaos engineering into the CI/CD pipelines. Some next level stuff. So we have two questions. I'm not sure if people want to unmute themselves. Tom Bone, do you maybe want to unmute yourself and ask the question, or can I just read it from there?
I can read them if people don't want to.
I don't. I can expand, but we could actually just read them off.
All right.
Yeah, if I need to expand, I'll definitely expand. Not a problem.
Yeah. Do custom experiments only run through the systems manager service, implying SSM agents would need to be installed to perform any custom experiments? SSM experiments, that's a specific category of actions, and to do those you need to have the SSM agent in place. The SSM agent is pre-installed on at least the Amazon Linux instance AMIs, and also on several of the Ubuntu and different Linux versions as well. So I'd say that it is pre-installed on most Linux instance AMIs already. But otherwise, yes, you would need to install that agent. That's correct. Would FIS service go as far as making an attempt to clone the state of resources that may be completely destroyed during an experiment? Do you mean that as a way to roll back to the state of a specific service or resource?
Yes, that's exactly it. So.
I would say no to that. What it can do is, for instance, start up instances again, for instance, but it would not do anything to go back to an exact state that an instance was in rather than running. So nothing on that instance, exactly how that instance was running, for instance, any specific services running or things like that. So the rollback actions in most cases mean to start something again, but then FIS would expect you to have things in place so that if something unexpected happens to an instance, it would then go back to the state you wanted to anyway.
Okay, I also have a question.
Yes.
I don't know if I missed this, but does FIS already have CDK support, or sorry, actually like CloudFormation support, which in turn means it can be CDK or not?
Yes, there is CloudFormation support for AWS FIS, so you can create your experiments using CloudFormation. That is correct. I don't think there is native CDK support yet, but since it has CloudFormation support, you're able to use it with CDK as well.
Okay.
Hi, I've got a question. I'm wondering how the FIS actually sends off the commands to the AWS API. I'm assuming it'd be the same as if I just sent them via the CLI myself. So if I had like an auto-scaling group or a ECS service, if I'm killing tasks or killing instances, I'm expecting that the auto-scaling group or the ECS cluster has no idea that there's an experiment being run, and therefore it should be doing things like the auto heal for itself. So I could use that in order to test that I'm actually building the AWS infrastructure correctly.
Yeah, that's right. What these experiments, they are run on the control plane level. So it is not exactly the same as if you would stop an instance through the AWS CLI. It is instead handled, let's say, backstage. So it is stopping or killing, terminating an instance that way. But testing, for instance, auto-scaling groups, that's one of the most common use cases we've seen so far. Customers using it as a way to make sure that the way they have set up their auto-scaling groups or clusters in some cases, that it works as intended, that if something happens to an instance, it will then scale or add a new instance, for instance.
Awesome. Okay. just one follow-up question, and I'll be done, I promise. The sample that you've got, do they by any chance have any recommendations that come with them to say, like, given this experiment, this is how you would overcome this particular problem?
They do not, because they usually when we create an experiment, we do it on the basis that something should work. So if I terminate instance X, my applications should still work. I'm not creating an experiment based on the assumption that something will break. And that's perhaps how chaos engineering has been marketed a bit in the past, that we're breaking things on purpose. But it's rather to validate or verify that something isn't breaking. We are stopping an instance to make sure that my application still works. So based on that, no, we aren't really able to give any recommendations on how to remediate those issues, because you should create an experiment that verifies an expected behaviors rather than an unexpected behavior. Was that a clear answer?
It is a clear answer. I'm just wondering that part of the AWS ethos is that there are certain ways that you actually build infrastructure to let's use the AWS infrastructure. And I'm wondering that if you have experiments that say, if you encounter this, this is kind of what the expected result would be. And the experiment is to really verify that your application doesn't break. So if you're getting breaks, then these could be common problems.
Yeah, well, I think that's really good feedback, because in many cases, for instance, we point a lot to the well-architected framework for how to build well-architected applications, and many services have their own recommendations. But tying those together, yeah, I think that makes total sense. It's not something that we do today, but I think that base experiments of how things should work, for instance, based on the well-architected framework, or for instance, a specific, as you said, auto-scaling group, create experiments that would test specifically that. Yeah, I think that makes sense. Something that we could look into.
Awesome. Thank you.
Thank you.
I have one last one, but I think I just answered it. So like you mentioned, that it only controls the control plane, like FIS only injects faults and things into the control plane. And I was thinking, but on that EC2 instance, we could actually look at that instance and see the CPU and memory rise and being maxed out. But that was still on the control plane, because first injected, or it like executed that SSM run document, and that then influenced the data plane, yes, and you could actually see it being going up in flames, but it was still coming from the control plane. It wasn't an actual service running on that instance that is made to do chaos for that instance, for that EC2. Am I right in saying that?
Well, with the SSM actions, they are being run on the instance. So, for instance, the CPU experiment we saw, those are the SSM agent running that specific SSM document on that instance. So that doesn't. It is started from the control plane, but then once it has started, it runs on that specific instance. So in that case, it's a mix.
Okay. Oh, do we have any more questions? If you want to pop them in the chat or ask them.
Questions, I can just carry on.
Sorry, Randy?
They're quite fascinating, this thing. Some of the most common issues that I've ever had with AWS is something like underlying hardware failure, when a machine just completely freezes up. It's not like dead, it's just completely inaccessible. And then obviously like an entire availability zone going down, and then you're left to figure out what's going on there. Is there anything in pipelines that would enable you to be able to test for those types of scenarios? Because I find those are usually the hardest things to test for.
Yeah. On the roadmap right now, there are a bunch of actions being planned, both for some of the same services that we have actions for today, and also for a lot of other services. So I can't really go into exactly which actions are hopefully delivered soon, but yes, we are planning on adding lots and lots of different actions and different services or support for different services. And the ones that are hard to test for yourself, for instance, turning off instances is pretty easy to test, but the ones that we would need to create, yes, those are definitely ones that we are focusing on.
So hopefully one day I can artificially just turn off an availability zone to make sure that all my stuff moves across and stuff. Because I think that's really the hardest thing that I've found is that you orchestrate all of this infrastructure, and then you go, well, I guess I'll wait for a production fault to actually check to make sure that what I expect to happen actually happens. And it's happened to me before where we expected it to all just move over, but because you have these split brain scenarios, it just doesn't work.
Yeah, I'm trying to answer this with the correct
I'm not
messaging.
expecting a full answer.
No. You're not the first one to. You're not the first one to ask for this. I can just say that, and it's definitely something we're looking into how we could address in best possible way.
Okay.
All that I can say is Elasticsearch, split brain is immediately what I think of if I Elasticsearch. So, yeah, good luck.
Yeah, no, they're tough problems, and I think something like what you're explaining, it's an amazing tool, and I can really see, I can even see us use. I mean, we're not exactly the biggest organization. We're trying to grow as fast as we can, but this stuff is very useful to put in while you're trying to build these very complicated systems. But I guess the lynch is still those underlying hardware faults, AZ availability being completely destroyed, or just random network faults. They're really, really, really hard to simulate when you are completely in the dark of the hardware. But I guess you guys have got access to the back of it, so maybe you can just like pull a power cord or something.
Yeah, automatic power cord pulling.
Yeah, just send a little robot, one of those little cars that you do in AWS racer things. Just go pull out power cords randomly in the data centers.
Yeah, you've figured out what we have the deep racers for. But one thing I just want to comment there is that it's never too early to start doing chaos engineering experiments as well. One thing that I often hear is that we're not big enough, or we're not far along enough to start doing this. I think the earlier you're getting used to doing this as a practice, I think the better. Start off small with these one-off experiments, do simple things just to verify that, for instance, autoscaling works as intended. Because otherwise, well, you will verify it that time something happens instead, but that's never the time when you actually want it to happen. So doing it in a controlled way, I think that's great.
And I think this tool helps you like save the time in doing, because it's not complicated to do. You've just shown it. It's really not that complicated to do like simple experiments.